We present differentiable programming for hyperspectral unmixing using a physics-based dispersion model. Hyperspectral unmixing is an important remote sensing task with applications including material identification and analysis. The central goal is to predict the presence or abundance of pure materials in a mixed sample from its spectral measurement. One of the key challenges facing this unmixing is the presence of spectral variability, where the spectra of various materials can change subtly due to a variety of factors. Here we show an example of this spectral variation for the same pure material, olivine. In this paper, we present a physics-based dispersion model as a way to realistically model and generate these spectra from previous literature. We incorporate this model into differentiable programming pipelines, namely an analysis by synthesis optimization and an inverse rendering convolutional neural network, to achieve end-to-end spectral unmixing. We validate our contributions on datasets in the infrared and visible to near infrared. We leverage a model called the Dispersion Model, which models materials with atomistic oscillators driven by electromagnetic waves impinging on the molecular structure. This describes the spectral curves generated by the material as a function of parameters, which control the shape of these curves. More details about the derivation of this model can be found in the main paper and the appendix. Using this model, we formulate an analysis by synthesis optimization that generates candidate materials or end-members for linear unmixing, and uses differentiable programming to optimize the model parameters as well as the predicted abundances. This method does not require training data in order to accurately perform spectral unmixing. Further, in the presence of training examples, we develop a convolutional neural network to perform inverse rendering and automatically determine model parameters and simultaneously perform unmixing for an enhanced performance and speed. To validate our contributions, we test on 3 datasets ranging from laboratory spectrometers to aerial and satellite imagery in the infrared and visible to near infrared spectra. We present numerous experimental results in the paper, including comparisons to state-of-the-art baselines across our 3 datasets, noise ablation studies, and even present new mineral visualizations with the Martian surface using our analysis by synthesis optimization. Please see the paper for more details. In summary, we introduced a physics-based dispersion model for the generative modeling of end-member spectra. We couple this with differentiable programming for end-to-end spectral unmixing via an analysis by synthesis optimization and an inverse rendering CNN. We validate these contributions with numerous experimental results on multiple modalities of hyperspectral imaging, showing outperforming state-of-the-art against baselines, and showing the benefits of combining physics-based methods with deep learning and machine learning for hyperspectral unmixing problems.